Hi, this is Stan Lyle with MasterMath. During the lesson, you're going to come to some You Try It slides where you're asked to do problems that relate to the lesson. Hit your pause button, try the problem, and then hit the forward key to move on to the answer. I hope you have a really good time today.
Today we're going to talk about exponential growth. Don't you love that word, exponential growth? Well, before we're done with this slide presentation today, you're going to understand what that means. And to give you a basic understanding, let's talk about a money example. Let's say that you invested $1,000 in a bank account, and the bank agreed to pay you 8% simple interest. That's 8% per year. So each year you'd earn 8% times your original investment of $1,000. After 1 year, they'd give you $80 and you have $1,080. After 2 years, they give you another $80 and you'd have $1,160. Well, that's pretty good. And if you graphed it, you'd see that the amount of money you've got is increasing, and it's increasing linearly. It's going up regularly, the same amount of change each year. Well, let's look at an exponential function. Compound interest is an exponential function. And basically the difference between simple interest and compound interest is this. In simple interest, you earn interest only on your original investment, $1,000 in our example. In compound interest, you'll earn interest on not only your initial investment, but on any interest that's accumulated in the account. In the case of this $1,000 investment at 8%, compound interest makes a huge difference. Look down here after 30 years. The increase after 30 years on a simple interest account is still $80 a year. On a compound interest account, it's almost $900. And if you graph that compound interest, you see it's not a linear relationship, it's an exponential relationship. Well, we got a lot to cover, and there's an awful lot of material here. And I put a brain break in the middle of this lesson, so you'll get a chance to take some time off and relax your mind. But before this whole lesson's over, you're going to understand what exponential growth functions are, what exponential decay functions are, and you should learn how to both write and graph exponential functions. We spent a fair amount of time talking about linear relationships, and you remember that y equals mx plus b is a basic formula for linear relationships. M is the slope, b is the y-intercept. B is the value of y when x equals 0. And if I had some data, x values and y values, I could create a formula in the form y equals mx plus b from this data. I'd first figure out what my rate of change, what my slope was, what m was. And I'd see that for each increase of 1 in x, I had an increase of 2 in y. So I know that my slope is the rise over run, or changes in y over changes in x. So it's 2 over 1, or a slope of 2. And I could figure out what my b was, what my y-intercept was, because my line would cross the y-axis where x equaled 0. And I could see that where x equals 0, y equals 1. So my b value is 1. My slope is 2. My b is 1. So my formula is y equals 2x plus 1. Well, now let's look at an exponential function. And the generic form of an exponential function is y equals a times b to the x power, where a can't equal 0, b has to be bigger than 0, and b can't equal 1. Y equals a times b to the x power is the generic exponential growth function. Now sometimes you'll see it written this way, y equals a times b to the t power. And that's because x is usually a time period. So sometimes we call that exponent x, but we can also call that exponent t for time period. Let's look at an example. This table represents exponential growth. And we can see that every increase of 1 in our x value results in a multiple of 2 increase in our y value. Every time we increase x by 1, we double y. You can see there's not a constant rate of change there. In the linear equation, every time we added 1 to x, we added 2 to y. In the exponential growth function, every time we add 1 to x, we double y. We could come up with an equation that represented this exponential growth. The first thing we'd need to do is figure out what our growth rate was, what our b was. Well, we can see it doubles. Our growth rate is 2. We can also see that our a value, our initial value, our value when the time period is 0, is 8. If we look at this function up here, y equals a times b to the x power, when x equals 0, b to the x is going to be equal to 1. A times 1 equals a. So y would equal a when x, or our time frame, is 0. Our initial value of y is the value where x equals 0, or in this case 8. So we can see that our formula is y equals 8, our initial value of y, times 2, our rate of change of y, to the x power, or the t power. Y equals 8 times 2 to the x power. Well, when x is 0 at our initial time period, y equals 8, because 2 to the 0 power is 1, so 8 times 1 is 8, and y equals 8. But after one time period, I'm going to multiply my 8 value by 2 to get my y value in the second time period. So in the second time period, y equals 8 times 2, or y equals 8 times 2 to the 1 power, to the first power. We've moved one place. Well, how about if we move 2 places? To go from here, a value of 8, to here, a value of 32, I've taken 2 steps in my x value, and I've taken times 2 times 2 in my y values. I've got times 2 twice, or times 2 squared. And if I go to my next value, I've got 1, 2, 3 changes in x, and I've got times 2 times 2 times 2, or y equals 8 times 2 times 2 times 2. That's 3 changes. That equals 2 to the third power.
Now you try this one. Hit the pause button, do the problem, and then hit the forward key to move on to the answer.
Okay, we've got a table and we want to try to write an equation that would describe this. And the first thing you want to do is determine if this is linear growth or exponential growth. And we can do that pretty easily. I mean, we can see that for every increase in 1 in my x value, I get a different increase in my y values. The first time I go up by 0.75, the second time I go up by 1.5, the third time I go up by 3. It's not a linear relationship. It's an exponential relationship. And we're going to have to force this into this generic equation, y equals a times b to the x. Well, let's first figure out our a. Our initial value of y equals a. What y is originally, before any time has gone by. When x equals 0, y equals 3. So our a value is 3. Y equals 3 times b to the x power. Now we got to figure out what b is. B is the rate of change. And we can see that our y values double every time we add 1 to our x value. So our b is 2. And the formula for this relationship is y equals 3 times 2 to the x power. Well, let's say you were asked to graph an exponential function, y equals 3 times 2 to the x power. And they also ask you to define the domain and the range of this function. Well, you'd probably want to create a table and create x values. I just went from -3 to +2. And for each of those x values, I calculated what the y value was. Now I need a graph. And then I can plot each of those points. I can plot -3, 0.38. And I can plot -2 and 0.75. And I can plot -1 and 1.5. And I can plot all the rest of those points. And I can graph this by drawing a line that best fit those points. And it looks something like that. And the interesting part about this line is it keeps as x gets smaller and smaller, this line keeps getting closer and closer to a y value of 0, but it never reaches a y value of 0. And we could define the domain and range this way. The domain, or the x values, are all the real numbers. The range, or the y values, are all the positive real numbers, because that line never goes below a value of 0 on the y-axis. Well, I'll tell you what, that's a lot of information, and we still got more to go. So I'm going to give you a brain break, a rest period. Hit your pause button, take a break, clear your mind, and then when you're ready to continue, come back and hit your forward key and move on to the lesson. Are you rested? Ready to get back to work? Good. Because we got a little bit of work yet to do. And first, I want to talk about the relationship described in this table. You can see it's not a linear relationship. As x increases by 1, y doesn't increase by a constant value. As a matter of fact, y decreases. Let's try to put this into a form of the generic exponential growth function. Y equals a times b to the x. And to do that, I need to come up with my initial value of y, my a value. My a value is my value of y when no time has changed, when x equals 0. When my time period is 0, my y value is 2. So I can put 2 in for a in the formula, and I'm partially on my way to completing a description of this relationship. Y equals 2 times b to the x. But now I need to figure out what b is. B is the rate of change. And I can see that every time my x increases by 1, my y increases by a multiple of 1/2. That's actually a decrease, isn't it? We're going to multiply y by 1/2 as we increase x by 1. So My b value is 1/2. And my formula is y equals 2 times 1/2 to the x power. That's a generic exponential decay function. Y equals a times b to the x power, but b is a fraction. B is greater than 0, but less than 1. B is a fraction like 1/2 or 1/3. And when b is a fraction, we're describing exponential decay. If we were to graph this function, it'd look just like this. As x increases, y decreases. Let's look at graphing real quickly. And I'm not going to go into a whole lot of this detail here because you're going to go into understanding graphs a lot more thoroughly later on. Let's just touch base on a few basic concepts. I've graphed 4 different exponential growth functions on this graph. The blue one is a function y equals 2 to the x power. And we call that the base function. All the other functions are variations of that base function, y equals 2 to the x power. The green line represents y equals 2 times 2 to the x power. It's just a multiple of 2 times our first equation. And we call that a vertical stretch of the first equation, y equals 2 to the x power. It's a vertical stretch because vertically, up and down our y-axis, we're going to double the impact of 2 to the x power. We're going to multiply our results in the first equation by 2. And that's going to stretch that first line so that the y values are higher in every instance. How about the yellow line? Well, the yellow line represents y equals 1/2 times 2 to the x power. And you can see that what we've done is every time we've got a y value from our base function, we've cut it in half. So the line won't be as steep as the blue function or the base function. And we call that a vertical shrink of our base function. And lastly, the red function, the red line, represents y equals -1 times the base function of 2x. In other words, we've just made all the y values negative in this red equation, and we call this the reflection of the base function. Let's look at a real-world example of exponential growth or exponential decay. Your brother purchases a used car for $3,000. Your dad says the car will lose about 20% of its value each year. That 20% is the decay rate. You understand that the car will be worth 100% minus 20% or 80% after the first year. 80% is the decay factor. 20% is the decay rate. Create a formula to estimate what the car will be worth in the future. Okay, we need to create a formula to describe this situation in this problem. And I can see that this is an exponential relationship. The value of y is decreasing by 20% each year. That's 20% of whatever the value was the previous year. So it's an exponential relationship, and it's going to be in this form. Y equals a times b to the x power. We can also rewrite that equation, and it might be more helpful or more easy for you to understand if we use the equation in this form. Y equals a times 1 minus r to the t power. We've changed x to t, and that's just to remind us that x is really a time period, or the number of time periods that we're talking about. And we changed b to 1 minus r. And that's just done so you don't get confused about decay rates and decay factors. The decay rate is 20%, But B is not 20%. B is the amount of value that's left after the time period. That's 80% in this case, or 1 minus the decay rate. Now, let's move forward and try to create an equation. Now we could do that with a table. We could say that x equals the number of time periods and y equals the value of the car. After 0 time periods, when the car was just purchased, it was worth $3,000. But after the first year, it had decreased in value by 20%, or it retained only 80% of its original value, and it was now worth $2,400. And that would go on each year. Now, if we wanted to put this into an equation, we would first need to figure out what our A, or our initial value, was. And I can see that initially that car was worth $3,000. So I could insert 3,000 for A, and my equation would be y equals 3,000 times b to the x power. Now I got to figure out what b is. B is 1 minus the decay rate. Every time I increase x by 1, I multiply the previous value of y by 0.8. So 0.8 is my b value, and I can write this equation, y equals 3,000 times 0.8x. But I don't need to create a table of values in order to calculate this equation. All the information I need is in the word problem. The word problem tells me my initial value for the truck, my value after 0 time periods, and that's $3,000. So I can plug that $3,000 in for A right there. And the word problem also tells me my 1 minus R, my 100% minus 20%. And I can just plug that 100% minus 20% into the equation right there where B goes. So without creating a table, I can look at this word problem and realize that the relationship is y equals 3,000 times 0.8 to the x power. Try this one. Hit your pause button, try the problem, and then hit your forward key to move on to my solution. Well, I can see that this is an exponential decay function, so I'm going to start out using the exponential equation. And it actually might be easier if I use this variation of the exponential equation. Y equals a times 1 minus r to the t power. And I need to remember what a means. A is the initial value of y. It's the value of y when no time periods have happened, when we're at the initial time. And I need to figure out what r is. And r is the rate of decay. And 1 minus r is what's left after the decay. So, let's start out with A. The problem says we start out with 128 players. So I can rewrite this equation as y equals 128 times 1 minus r to the t power. The problem also says that each day, each time period, I lose 50% of the players. So my rate of decay is 0.5. And I can rewrite this as y equals 128 times 1 minus 0.5 to the t power. Now, I can simplify 1 minus 0.5 to 0.5. And then I can calculate how many players would be remaining after 5 days. 5 days is my number of periods. It's my t. So I'll substitute 5 for t. And then I'll calculate what y equals 128 times 0.5 to the 5th power is. And I'll discover that after 5 days, I have 4 players left. That's our lesson on exponential growth and decay. I hope you learned a lot. Now it's time to test your skills. Go to www.mastermath.info, and there you'll find some worksheets and quizzes on exponential growth and exponential decay. Hope you had a good time. Hope you learned a lot. And I hope we see you again real soon.